US Physics Olympiad year 2011 USAPHO Semifinal Exam. This exam consists of 2 days, each day for 60 minutes. First day there were 4 problems, which was part A, and the second day was 2 problems, part B. Problem A1. Solutions for all problems you can find below this video in the reference of the description. Single bubble sonoluminescence occurs when sound waves cause a bubble suspended in a fluid to collapse so that the gas trapped inside increases in temperature enough to emit light. The bulb actually undergoes a series of expansions and collapses caused by the sound wave pressure vibrations. We now consider a simplified model of a bubble undergoing sonoluminescence. Assume the bubble is originally at atmospheric pressure E0 equal 101 kilopascal. When the pressure in the fluid surrounding the bubble is decreased, the bubble expands isothermally to a radius of 36 microns. When the pressure increases again, the bubble collapses to a radius of 4.5 microns, so quickly that no heat can escape. Between the collapse and the subsequent expansion, the bubble undergoes isochoric constant volume cooling back to its original pressure and temperature. For a bubble containing a monatomic gas suspended in water of temperature T equal 293 Kelvin, find A. The number of moles of gas in the bubble, B. The pressure after the expansion, C. The pressure after collapse, D. The temperature after the collapse, and E. The total work done on the bubble during the whole process. You may find the following useful. The specific heat capacity at constant volume is CV equal 3/2R. The ratio of specific heat at constant pressure to constant volume is gamma equal 5/3 for a monatomic gas. Solution. To start solving this problem, first let's draw the VP diagram for this process. Initially we have point 0 with a initial unknown volume, but in point 1 we have a known volume which has a radius 36 micrometers, and that was isothermal expansion. After that it was adiabatic compression, and because this process is adiabatic, it means that this curve increasing much faster, so it reaches point 2, which is higher than point 0. That's new pressure with the same volume as in point 0, and that was volume with the radius 4.5. So we know what is volume in point 0, we know what is temperature in point 0, and we know what is pressure in point 0. From this data we can find what is number of moles in this bubble. For that we use ideal gas law. This is our equation. Now we can find what is number of moles. That will be in point 0 pressure multiplied by volume divided by R, and temperature T. So when we put numbers, we will get 1.58 multiplied by 10 power negative 14 moles. That was answer for question A. Question B. Find the pressure after the expansion. It means that in point 1. Here we have isothermal expansion. So we have this isothermal equation. P0 V0 equal P1 V1. So from here we can find what is P1, pressure in point 1. So P1 equal P0 V0 over V1. After when we put numbers, we will get 197 pascals. So that's the answer for question B. Next question is C. The pressure after collapse in point 2. So here we have adiabatic compression. We have this formula for adiabatic compression. So from here we can find what is pressure in point 2. So using this adiabatic formula for adiabatic compression, we can find what is pressure P2. That will be 6.46 10 power 6 pascals. That was answer for question C. Question D. We need to find the temperature after collapse in point 2. So here we have same volume, and in point 2 and point 0, and we know what is temperature in point 0. So we have pressure proportional to temperature. So temperature will be T0 multiplied by P2 over P0, which is these numbers. So that will be 1.88 by 10 power 4 Kelvin. So that was the answer for question D. And the last question E. The total work done on the bubble during the whole process. So during isothermal expansion, gas doing positive work from point 0 to point 1. It means that on gas there is negative work, which we mentioned by sign negative. And this is the expression for isothermal process. So that will be just a logarithm of this relation between V1 and V0, and finally we can put numbers and get this result for work done on gas in process from 0 to 1. Next process is adiabatic compression, and during adiabatic compression the total heat is 0. It means that all work done by gas, it's going because of change of internal energy, and we just need to find what is a change of internal energy for gas from point 1 to point 2. So total change of internal energy equal N multiplied by CV, not delta T, where delta T is T2 minus T1. Finally, that will be 3.64 times 10 negative 9 joules. And total work on gas, so that will be answer for question E. W1 plus W2, which is equal 3.40 10 power negative 9 joules.